I'm Seth Bergmann, and this is part 3 of my introduction to the analysis of algorithms. If there's anything that's unclear as I go through this tutorial, feel free to download my free book from rdw.rowan.edu. Do a search for Bergmann. There's a book on Introduction to Computer Science there. So I'll continue developing my series of Java methods in which we're discussing the big O analysis of the runtime, how much time it takes a method to run as the size of the input gets large. So the next method is I'm going to call M10, and the input is just an int called n, and so the size of the input is the size of that parameter n, and I'll set up a loop here while n is greater than 0. Do the following: print value of n, and we'll also take n and divide it by 2 and store the result back into n. So there's the body of the loop. And what will this print? It will print, if the parameter n is 8, it will print 8, then 4, then 2, then 1. How many times does the print statement execute? It depends on n. If n is 8, it'll print 4 times. If n is 16, it'll print 5 times. If n is 32, 6 times. How many prints will there be as a function of n? Log base 2 of n. And normally in computer science, when we talk about logarithms and we don't specify the base, as in this case, we mean base 2. What that means is that we can double the size of the input, and if we do that, we'll get only one more iteration in the loop. That's a fast algorithm, when we can double the size of the input and it will cause only one more iteration. So we say the runtime is big O of log of n. My next example will have to do with the Fibonacci sequence. That sequence is the sequence of whole numbers 1, 1, 2, 3, 5, 8, 13. Each number in the Fibonacci sequence is the sum of the previous 2 numbers. So if we had a method named fib to give us the value of the nth number in the Fibonacci sequence, fib of 1 would be 1, and fib of 2 would also be 1. But fib of 3 would be 2, and fib of 4 would be 3, etc. So we can say, we can define a method now to find the nth number in the Fibonacci sequence. It'll return an int. Name of the method is fib, one parameter n. And I'm going to write a recursive method here. If n is less than 3, I'll return 1. So if n is 1 or if n is 2, return 1. Let me describe this a little better. Return the nth number in the Fibonacci sequence. If n is not greater than 3, I'll return the sum of fib of n minus 1 plus fib of n minus 2. Okay, so how many calls to fib are there? Well, to get fib of 3, I have to call fib of 2 and add fib of 1. So there are 2 calls to fib there. If I call fib of 4, that's going to be fib of 2 plus fib of 1. Fib of 4 is going to be fib of 3 plus fib of 2. So I have 2 calls here, and then fib of 3 there are 2 calls, so it's a total of 4 calls to fib. And then with fib of 5, for fib of 5, I have 2 calls to fib here, fib of 4 plus fib of 3. And in fib of 3, I have 4 calls. In fib of 2, I have 2 calls. So that's 6 and 2 is a total of 8 calls to fib. So for fib of n, I will have approximately 2 to the power of n, 2 to the power of n plus 1 here, actually. Sorry, n minus 1 calls to fib. This means that increasing the input by 1 doubles the number of calls to fib. That's expensive. That's a fast-growing function. Big fib is big O of 2 to the power of n. I'll use this pointing arrow up to represent up power because I do not have exponents here in TextEdit. The way I've written fib, it is big O of 2 to the n. And algorithms which are big O of 2 to the n, we say are hard. More precisely, if a problem is given and the only algorithms we can find to solve that problem are big O of 2 to the n, then we say that the given problem is hard. It will just take too long to find a solution for a moderately large size of the input. That is the third part of 3 parts to the introduction to the analysis of algorithms. Again, if any of this was unfamiliar, there's a free download at rdw.rowan.edu. Search for Bergmann.